Okay, guys, good morning. Hope everybody's doing well today on this wonderful Monday. If Mrs. Leroy has not already done so, she will be returning your test from last chapter, and I am allowing all students to correct this test to receive some additional bonus points on their score. Those corrections will be due tomorrow morning at the beginning of chemistry class. So make sure on a separate sheet of paper you correct that test, and you also need to put the page numbers where you got the corrections from. That's the only way I will count those corrections. Each correction is probably going to be worth around a point, so make sure you get that completed. As you guys see on the screen, I wanted to go ahead and start this morning by just doing a quick review over the first section that we talked about last week, defining acids and bases. And if you guys can recall, we talked about 3 different definitions. The first definition we talked about was the Arrhenius acid and base. And you can see on the screen the definition. Arrhenius acid releases hydrogen, and the Arrhenius base releases hydroxide, the OH negative. The Brownston-Lowry acid, it donates a proton, and then the base accepts a proton. So those are in terms of protons. The Arrhenius were in terms of ions. And then the final one, the Lewis, an acid is defined as something that accepts electron pairs, and then a Lewis base definition, as you guys can see again on the screen, donates electron pairs. Remember in our discussion we drew a circle. We said Lewis was the most broad definition, so make sure you remember that, and hopefully this little quick review will help. You can take your textbooks, ebooks, open up to page 402. We're going to start there today talking about water. We've already talked about it a little bit, the ionization process. So acid-base equilibrium, this is the first section. We talked about this last week. Just a quick review again. We talked about how water reacts with itself, H2O plus H2O, which would give us the 2H2O on the reactant side. And then you have the equilibrium and with the hydronium and with the hydroxide ion. H3O positive is hydronium, and then the OH negative is hydroxide. And we talked about how that process works. We also went back to the previous chapter and explained how this is set up in an equilibrium constant. And you guys remember it's the molarity per concentration, moles per liter of the hydronium times the hydroxide divided by the 2 moles of the water. And we also recall that water is equal to 1 because it's a liquid, so it's a constant of 1. So we take that out of the equation and we get the KEQ equals the hydronium ion times the hydroxide ion, which is called the ionization constant of water, and it has the symbol K sub W. So again, that's all review from last week. That is extremely important, and you got to make sure you know what the ionization constant of water is. It's equal to the molarity of the hydronium times the molarity of the hydroxide. So again, make sure you memorize that equation. And then we talked about what it is actually equal to. The ionization constant of water is actually equal to 1.0 times 10 to the negative 14th power. And we worked this a little bit last week. Do remember that it only is at 25 degrees Celsius because when you change the temperature, it's going to have an effect on the ionization. How it could either speed it up or it could slow it down because it's one of those stresses on the equilibrium with Le Chatelier's principle that we talked about last chapter. So if you know that the hydronium ion is 1.0 times 10 to the negative 10th, you can immediately solve for the hydroxide ion because the exponents have to be equal to 14, negative 14 specifically. So negative 10 plus what equals negative 14, and that's negative 4. So it's very easy to figure it out. If the hydronium ion is 1.0 times 10 to the negative 3, well, what plus 3 is 14? Yes, that is 11. So the hydronium ion is equal to 1.0 times 10 to the negative 11th. You'll have to be able to do this. It's pretty simple, but make sure you're able to be very, very proficient at this. Just a quick sample problem here. It says the concentration of the hydronium ion, again, hydronium is the H3O with a positive, is in a mild acid is found to be 5 times 10 to the negative 7th moles per liter. So that's the molar concentration. So the way we figure this out is, it's the question that's asked is what is the concentration, again that's molarity, of the hydroxide ion? Well, we're going to use the ionization constant of water, because we know that that is equal to the hydronium ion times the hydroxide ion. So I go ahead and solve the equation for the for the hydroxide, the OH. So you guys just use basic algebra. You just divide both sides by H3O positive. So that's what I did here, and you can see divided both sides and just flipped it around. The hydroxide ion is equal to the ionization constant of water divided by the molarity of the hydronium ion. And then the next step is to plug in your numbers, because we know the values for these two pieces. We just talked about what the ionization constant of water is. That is 1.0 times 10 to the negative 14th power. The problem also gave us the hydronium ion. It told us that it was 5 times 10 to the negative 7th. So you can see, just substitute them in there. Use your calculators to punch that in and get your answer. Again, this is a good place to remind you, you will only be able to use calculators that are not on your iPad. So make sure if you haven't purchased one yet, you get a cheap scientific calculator at Walmart or the dollar store. Very inexpensive, but you need to go ahead and do that. Some of you had trouble punching this in your calculator, depending on your calculator. And I said you're looking for a times 10 to the X button. Not all of them have that. A lot of your Texas Instruments will have two E's, capital E and capital E. When you push that EE button, it'll display E on your calculator. That E stands for times 10. So the way I would punch this into my calculator, if it's a Texas Instrument, is 1. Then I'd hit my EE button, and then I would hit minus, then the minus sign, not the subtraction sign, but the negative sign, 14, divided by 5 EE, negative, again, not the subtraction, but the negative sign, 7. And when you punch that in your calculator, you should get 2 times 10 to the negative 8th molar. So make sure you put that capital in there for molar. So that's pretty much how you work with the ionization constant of water. It's not too bad. It's pretty basic, but very, very important. A couple things here. Since we know that the ionization constant of water is 1.0 times 10 to the negative 14th, and that the ionization constant of water is equal to that formula there that you see, we can assume a couple things, or actually figure out a couple things, because we know that water self-ionizes, meaning it reacts with itself to give you hydronium and hydroxide. So what this means is these two pieces must be equal. Okay, the values must be equal in just standard water. So this is where I get this equation, and you also can see them working this out on the bottom of page 402. Since they're equal, they are equal to 1 times 10 to the negative 7th times 1 times 10 to the negative 7th. Just a general thought here. This means that 1 out of every 555 million water molecules are ionized at any given instant. So water is constantly reacting with itself and forming ions, as we've already talked about. All right, on page 403, it introduces something extremely important called the pH scale. You must know this. This is how a lot of the application in the chapter is going to come from this section. So please pay close attention to what we're going to be talking about. The pH stands for power of hydronium ion. So that's what actually pH stands for, power of hydronium ion. And we just abbreviate it by pH. pH is a negative logarithm of the hydronium ion concentration. Okay, so the question is, what does this mean? All right, so it gives us this formula. This is the formula you must get down. It's very important, okay? pH is equal to negative log of the hydronium ion concentration. So if you know the hydronium concentration, let's say, like in the last problem, we figured it out, and it was 2 times 10 to the negative 4, I believe is what your final answer was. That's what the hydronium concentration is. So you could actually plug that in this equation to figure out what the pH is. So it's a very important process. Look on your calculators. You should see the word log, L-O-G. That's abbreviation for logarithm. And that all that means is power of 10. Okay, so don't be confused by that. It's actually pretty simple. A lot of students get confused by it. But if you say 10 to the second or 10 to the fifth, or 10 to the 7th, whatever, that's what log stands for. It's just another way to calculate it on your calculator. You need to use the log button for this part, okay? So let me show you an example real quick, okay? It's actually pretty basic here. You really don't even have to plug it in your calculator because you know something. If the hydronium ion is equal to 1 times 10 to the negative 7th, then you know that the pH is equal to that exponent. It's equal to 7. Okay? Now the only time you can do this is when it's 1 times 10 to something. If it's 5 times 10 to a different power, you actually have to use the formula. And we'll get to some of those in just one moment. Another example, if it's 1 times 10 to the negative 8, then you know that the pH is equal to 8. If it's 1 times 10 to the negative 4th, then you know that the pH is equal to 4. Okay, it's the opposite signs there, as you can see on this slide. The reason it's opposite is because if you guys remember the equation on the previous slide, or if you look in the textbook on 403, right smack dab in the middle where you see the equation, you see what I'm talking about. You have the negative, so the negative log, that negative negates all these exponents and makes them positive. So that's how that kind of works. Okay, very important pH values here. A pH value of 7 means that it is a neutral solution. You got to get this down. There's a picture at the bottom of 403 that can help you understand this. But a pH of 7 means a neutral solution. All right, a neutral solution. A pH of 0 to 7 is an acidic solution. So if we go back to what we talked about with acids, the litmus would turn red, and that's kind of why on that picture at the bottom of 403 it's red for all the numbers 0 through 7. pH of 7 to 14 is a basic solution. Okay, that's why it's blue on that little arrow chart that you see at the bottom. So make sure you understand when you're calculating a solution's pH, you are able to determine if it's a neutral solution, acidic, or basic neutral solution. So you'll have to do that. You'll have to calculate the concentration and then tell me, is it neutral, acidic, or basic? Here's that chart I was talking about. Just kind of visualize it there. Neutral is 7, acids are 0 to 7, and bases are 7 to 14. Okay, so let's look at a sample problem and see how this works. It says the hydronium ion concentration in a shampoo is 2.0 times 10 to the negative 5th power, molarity. So this is the hydronium's concentration. Okay, everybody hopefully follow along here. This is the concentration. So we look at our formula to figure out what the pH is. Okay, so here we go. That's the formula for pH. pH is equal to negative log times the hydronium ion. Well, the problem told us what the hydronium ion was. It's 2.0 times 10 to the negative 5. So on your calculator, you can go ahead and punch that in. I would recommend to punch in log, hit the log button, 2.0 if you want to add that, EE, the minus sign, not the subtraction, but the negative sign, 5. Again, don't worry about this negative out here. I'll explain why in a second. Hit the log button. It should display log if it's a display calculator. It'll say log. 2.0 EE, negative sign, 5. Hit equals, and you should get 4.7. Now, more than likely, you should have actually gotten a negative 4.7. The negative 4.7, but that's why this negative is out in front, because obviously y'all know negative times a negative is a positive. Okay, so you should get 4.7. So again, if you didn't, go back, let's try it again. Don't worry about this negative sign. Okay, you just negate whatever you get when you plug this in. Hit log 2.0 EE negative 5. And when you punch equals, you should get negative 4.7. But again, you have that negative out in front. Negative times a negative is a positive. So this shampoo has a pH of 4.7, which means if I ask you, is it acidic or basic, you would say it's acidic because it's between 0 and 7. That's all you have to do. Not too bad. What is the pH of an aqueous solution? Of 40 grams of hydrogen iodine dissolved in 500 milliliters of water. Okay, this one's a little bit more in depth. If you want to see exactly what it does, it's actually example 16-3 on page 404. So you can follow along there if you need a little bit of help. This one's different because it doesn't give us a concentration. If you look at the problem, it says nothing about the hydronium ion's concentration is. It doesn't tell us any of that. So we have to figure that out. And that's what we're going to do first. Okay, so first convert grams of hydrogen iodine to moles of hydrogen iodide. This should be very simple. We've done this all year. We would use the gram molecular mass to calculate this. So you look on a periodic table of elements, find hydrogen, atomic mass, write it down. Find iodine, write it down. Because that's what I'm going to do. I'm going to say 40 grams of hydrogen iodine. There's the gram molecular mass right there, 127.9 grams, and we know that that's equal to 1 mole. Okay, you may be asking the question, why do I have to go to mole? You have to go to mole because remember, hydronium concentration is molarity, which is moles per liter. Okay, moles per liter. So this takes the 40 grams and it converts it to moles. That's what I wanted to do. Now what you guys have to do is you have to convert the amount that you were given to grams. All right, I'm sorry, to the actual amount, the volume, into liters. And so there you can see that cancels. You get a 0.003 moles of hydrogen iodide. Now, next you have to calculate the molarity, as we just talked about, moles per liter. So you take that number that was given and you divide it by 500.00 milliliters. I got the 500 from the problem. Look in the textbook and you can see it said I'm dissolving the 40 grams in 500 milliliters of water. So that's where I got this 500 milliliters. This is the molarity divided by 500 milliliters, and then it's a simple conversion to liters. So 1,000 milliliters is equal to 1 liter, and then the milliliters cancel out, and I end up with 6.3 times 10 to the negative third molal solution. It seems difficult, but it's very simple if you think it through. You take the mass, the original stuff given that you poured into the beaker that have 500 milliliters of water. You convert that mass to moles, and then you convert the amount of water you had to liters, so you can get moles per liter. So that is the amount of hydronium in this particular substance. So now I can go to pH. pH is equal to negative log of the hydronium ion. That's the value of the hydronium ion, so that's what I'm going to plug into the equation. And there you go. So you plug that in. Now, on your calculators, again, take your calculators out, find that log button, LOG. So log, and then you're going to hit 6.3, and then EE, and then don't hit 10. You just hit the the minus sign, not the subtraction sign, but the negative sign. 3. Hit equals on your calculator. It'll display negative 2.2. Just remember, it's negative. You want to make it a positive, so your final answer is 2.2. So again, you know that this particular solution is acidic. All right, moving right along here. It's not too bad. You'll get the hang of it, I promise. It's really not too bad. Here, if the pH is 7, then the hydronium is 1.0 times 10 to the negative 7th. The ionization constant of water is 1.0 times 10 to the negative 14th. And it's just a review that if these two pieces, that number there, the negative 7, has to add something to it to get that negative 14. So negative 7 plus negative 7 equals negative 14. All right, what if the pH is 2? Well, I'm glad you asked. The hydronium is equal to 1.0 times 10 to the negative 2nd, because remember, the pH and this exponent are the same. It's just this is negated. So I'm asking you guys the question, what is the hydroxide ion equal to? Well, what plus that negative 2 will give you negative 14? Well, you guys are right. It's negative 12. So the hydronium ion is 1.0 times 10 to the negative 2nd. The hydroxide ion is 1.0 times 10 to the negative 12. All right, question here. What does the pH equal if the hydronium equals 1 times 10 to the negative 10th power? All right, this should be very fast. You don't have to do any kind of calculations because you should know pH is directly related to hydronium. All right, give you a second. It should be number 3. Yes, it is, because this is negative 10, so the pH is the positive of that, which is 10. Very simple. All right, let's move on to something else called POH. POH is just like pH, except instead of using the hydronium concentration, it's going to use the hydroxide concentration. That's why it's called POH, because this is hydroxide. It's the same exact method. Okay, so nothing's changed except what you start with. Now see, because I could give you the hydroxide ion. Here the hydroxide ion is 1 times 10 to the negative 9th, so the POH is 9. Just like if this was hydronium H3O, this would be pH. But this is hydroxide OH, so it's POH. This is 9, this is negative 9. Alright, if it's negative 3, 1 times 10 to the negative 3rd, the POH is 3. And you can see it's the same thing that I just showed you, except it's just POH instead of pH. pH is the power of the hydronium ion. POH is the power of the hydroxide ion. Okay, so here we go. What does the POH equal if OH negative equals 1 times 10 to the negative 10? Well, POH and the hydroxide ion are very similar. Remember, it's just you take this and change the sign. So it is 10. All right, POH and pH. We already know this information, but this is new right here. This is very, very, very important, so please get this down. Because we have all this information about the ionization constant of water, we know something. We know that the pH plus the POH, it must be equal to 14. Get that down in your notes. It's very, very, very important. pH plus POH is equal to 14. So if I tell you the pH is 10, then you should know immediately that what plus 10 is 14? 4. So the POH is 4. If I tell you the POH is 7, well, let's not do 7. If the POH is 12, what plus 12 is 14? 2. So the pH would be 2. Very simple formula there, but very important and very effective. Here's a simple example. If pH is 5, then the POH is then the hydronium ion is equal to 1.0 times 10 to the negative 5th. And we then know that the hydroxide ion is 1.0 times 10 to the negative 9, because this number and this number have to equal negative 14. So the POH is 9. Well, you could have told me that at the very beginning, because the pH was 5, so what plus 5 is 14? That would be 9. Alright, if the pH is 2, the POH is 12. Again, 2 plus 12 is 14. If the pH is 10, then the POH has to be 4. Very simple. pH plus POH is equal to 14. Alright, you see a little chart on, let's see, what page is it on? Top of page 4 or 5, that will be very helpful for you to know. So you want to make sure you understand this. This is how you convert from piece to piece. I can go straight from pH to POH. I can go straight from hydronium to hydroxide. That's very simple. The tricky part is, how do you get from hydronium over to POH? Well, you got to follow this scale. You first have to go to pH, and then you could go over to POH. What happens if I give you the pH and I ask you for the hydroxide ion? Well, you could go this direction and then over, or you could go from pH to POH and then down to hydroxide. Just depends on how you want to go. But this is a very helpful flow chart that will help you understand what you will be working on in this particular section. All right. Okay, here's how I do this. All right, so I'm going to show this problem, and then I'm going to let you guys work on some things by yourself. Basically here, what we want to look at is calculate the pH, POH, and the hydroxide ion for a 0.0001 molar hydrochloric acid solution. So the first thing you want to do is rewrite this in scientific notation. So move the decimal place over 4 places. That'd be 1 times 10 to the negative 4th. Okay, so y'all tell me, I know I'm not there, but you can still answer aloud, if the hydronium, the H3O, is equal to 1 times 10 to the negative 4, what is pH equal to? All right, I'm hoping everybody said 4, because remember, this is and this are the same, they're just opposite signs. Okay, so I found the pH. Now I can go from pH to POH, because what is the POH if the pH is 4? Well, remember what the sum of pH plus POH must be equal to. It's got to equal 14. So what plus 4 is 14? Well, you guys are smart enough to know that's 10. Okay. Now what you have to do is you have to go from POH to the hydroxide ion. Okay. Well, remember, just like this one, it's 1.0 times 10 to the negative 4, and that's 4. Hopefully you can go very quickly from this to what the answer will be. Well, this would become the exponent, and you just negate it. So it's 1 times 10 to the negative 10th power. Very easy application if you know a couple of pieces. This exponent, the negative exponent, you change it, make it positive, and pH and hydronium go together. And then you have what plus 4 is equal to 14, because the pH plus the POH is 14. So that'd be 10. And then this has this same relationship. The 10 has the same relationship to the 4 and to the negative 4. So hydroxide would be equal to 1 times 10 to the negative 10th. Whatever this number is, you negate it and put it as the exponent. Very simple process, but very, very important process. And this is going to be a lot of the application in this particular chapter. Okay? All right. I hope that helps with this particular component to the chapter. All right. What I want you guys to do for homework tonight, I want you to go to the chapter review, and you guys are going to be working some of these pH problems to help give you practice. Okay. All I want you to do is let's see here. I want you to do number 25 and 20. Let's do 24 and 25. Okay, 24 and 25 in the chapter review, and that should give you some good practice for this particular part of the chapter.